Someone asked if there's another one. I believe there is, but I'll double check for you after we do these 3 questions. Also, I'm sorry if Bear barks a lot in the background. He's having a day. All right, so this one is a multiple substitution one, and so it's a really common one for the exam. So first thing we have to do, I'm going to zoom in real close. We're going to circle NH2, and you guys are going to tell me, is this an activator, a weak deactivator, or a strong deactivator? Yep, it's the strongest activator. So where does it direct? Orthopara. Okay. And then for chlorine, what do we think chlorine is? It's a weak deactivator, and it is orthopara, exactly. And someone asked the question in the chat. I'm going to answer you. I'm just going to do it after we work through it so it doesn't like spoil the answer. Okay, so we know that between these two, the stronger activator is going to be the one that is the director. So we know that NH2 is going to be the strongest activator. And so compared to NH2, we are going to want to substitute the ortho positions or para, but para is already taken. So in our answer choices, we already know that 1 is like ridiculous because what is even happening here, right? It just moved the chlorine around. So we know that that's not going to work. And then 2 looks kind of weird, but it is reasonable, so we're going to leave that. For 3, they did ortho to chlorine, and we know that's not what will happen, so we're going to go ahead and get rid of that. This one looks pretty reasonable. And then the last one, we know that that doesn't make sense because one of them added ortho and one of them added meta. That's not going to happen. We'll cancel that one out. So now between 2 and 4, 2 and 4, this is the one where it gets a little bit weird because if we have an NH2 on the ring and we react with Br2 and H2O, someone also pointed out that it's H2O, not FeBr3, exactly. So if you have Br2 with H2O and an NH2, it's actually going to add fully. That's what we call it. We say it substitutes fully. And that just means it's going to substitute all of the favorable spots. So in this case, we have 2 ortho positions. It's going to substitute both of those ortho positions, not just one. And again, that's only in the case of NH2 with Br2 and H2O. So when we have NH2, Br2, H2O, we are going to substitute multiple times at all of the favorable spots. In this case, it would be both ortho positions. So the answer in this case will be number 2. The question was, what if there was no NH2? So this is only going to happen because of the NH2 present. NH2 is so activating that it will make the reaction happen multiple times, essentially. And then someone said, are there any other reactions like that? I'm sure there are, but we're not going to talk about those because this is the only one I've ever seen Dr. West put on his exam. We could have also used chlorine, iodine, fluorine, and whatever other halogen. But pretty much it's just going to be these things. So NH2, a halogen, and H2O. And then someone asked me to repeat that, and I will do that. Let me just see if there's any other questions. Okay, someone said, like, what if there was Br2 and H2O, but not NH2? So again, this is going to happen only when you have an NH2, a Br2, and an H2O, because NH2 is such a strong activator. It's going to activate the ring so much that when you have this set of reagents, it will fully substitute, aka it will substitute all of the positions that the director is directing to. So in this case, both of the ortho positions will be substituted, and so we will get this product. So I'm sure there's different exceptions and different reactions where similar things would happen, but in this class, the only time we're thinking about polysubstitution like this is in the case of NH2, Br2, H2O, and alkylation. One second. Sorry, my sister was giving me my charger. So does this make sense? I can go over it one more time if you guys need me to. Just let me know. Make sense? Okay, sweet. And someone said, so without NH2, it would only be one Br that is substituted? Exactly. So let's say we had an OH. That's an activator. And a Cl. And again, we do Br2, H2O, or FeBr3. At that point, it doesn't matter. So we still have our ortho-para director, and it's an activator. Our ortho-para director, but it's a weak deactivator, so the OH is still going to choose, or OH is still going to direct, I should say. And it will still direct ortho-para. But in this case, we no longer have that NH2, so the answer here would just be like this. Or on the other side, it would no longer be both. That would be very unlikely. And I'll zoom out a little bit. You're very welcome. Why is there H2O? Honestly, I don't know that or why that is. And I don't know that it's even a big thing. It might just be that it's, a catalyst that's sometimes used. Usually for these reactions, it's going to be FeBr3 or AlCl3 or H2SO4 because it's a strong acid. But the only time they really ever ask you for H2O is in this reaction specifically. So I kind of tell you guys to group those together and think of it as one thing. And someone asked, would it be the same product formed if FeBr3 was there? I believe it would be, but I'm not 100% sure. Just because, again, I always see kind of these three things clumped together and we get this kind of reaction that I mentioned before. But I think FeBr3 would be the same because it has the same properties. You're welcome. Okay. So I believe the next one you wanted to do was number 7. I don't know why it goes from 4 to 7. That's really weird. All right. So first thing is first, Tert-Butyl Benzene. I don't think this will be likely to show up on the exam. But if you guys really, really want, we can go over it, but I don't think it's going to show up on the exam. Let me know what you think. Do you want to go over it or go on to something else? Great question. Someone asked, how do we know which questions we should know? I am going to go through it, and I think I said I'll give that to you guys today. But essentially just go through it and look and see if you guys have seen that in lecture or with me, because well, first primarily lecture, because that's what, he tests you on. But for example, if you look at the first page, rate determining step, we for sure talked about that one. So this is a good question. Something like this, it's a little bit wordy, but it's essentially just asking you about what kind of catalyst you use. So this is a good question. 4 is an okay question. And then you go to 7 and you see a double bond with H2SO4 or something like this with an H2SO4. This is the only one that is from this chapter, right? Or from even Orgo 2, I'll say. So this one isn't really a great question because we haven't looked at these reactions really in Orgo 2. They were more of like Orgo 1 reactions. And it's the same thing here. We've looked at this one, we've looked at this one, but these two are kind of like Orgo 1 type questions. We don't want them. Same with this, like the peroxide or the 400 degrees Celsius, the double bond, that kind of stuff is not really from Orgo 2, so I wouldn't prioritize this question because we haven't really looked at that material in Orgo 2. And then another question was, will he throw past chapters on there like NMR and stuff? He doesn't usually do that because the exams are not cumulative until the final. The final is the only cumulative exam in this class. So the only NMR kind of question that shows up on this exam is he'll ask you something like, which of the following is true of benzene, right? And you are expected to, like, there's a couple different answer choices, obviously, that he could put on there. But the general concept you have to know for a question like that is benzene has all of the hydrogens as being exactly the same. So all of the hydrogens are exactly the same on benzene. It will only have one NMR signal. And we knew that in the NMR chapter, but now we know that to be true because all of the electrons are fully delocalized. And so all of the environments are exactly the same. And one other thing that I'm going to draw out for you guys, because it's kind of weird, but we have these two structures for benzene, right? They're almost exactly the same, but the double bonds were flipped around. What do we call these two structures? Like compared to one another. Yes, someone said they are, I don't remember how to pronounce this, to be honest. I think it's Ketol structures. But these are resonance structures. And the reason I bring this up is because these two structures, which are resonance structures, are not correct. So what I mean by that is neither of these are accurate depictions of benzene. So there will be a question either now or on the final. It always shows up. And it will ask you something like, which of the following is true about Ketol's resonance structures for benzene, right? So you know he's talking about these two. And you know that neither one are technically correct because in reality, all of these electrons are completely delocalized around the ring. And it's not going to be stuck in these specific positions. Those are just ways to depict it. And someone exactly said it's because the hybrid structure would be the true structure. So this would be the hybrid of these two resonance structures, and it will be the most correct. So that's the only kind of way that old chapters really come back. He sent Katrina and I an email about like what will be on the exam. And let me just pull it up before I say anything so I don't lie to you guys. But he did say like nothing, none of the reactions will be present from previous exams. So I was going to show you guys this in SI today, but since you guys are here, why not? So yes, he said no Grignard reactions will be there. The only reactions are going to be the diol reaction, the acetone ketone reaction, the amine reactions, and the Wittig reaction, which we haven't done yet. And the rest of it is pretty much just going to be electrophilic aromatic substitution reactions. And that's pretty much it for reactions. And then other than that, it's just going to be conceptual stuff about chapter 14 and chapter 15 and 16. So yes, all the videos and recordings and stuff are posted on YouTube. I posted all of the recordings from this week on YouTube yesterday, and I have been recording like those little like informational video things, and those will be up at some point. Do we need to know polycyclic aromatic compounds? So all you really have to know is that, sorry. Sorry for all the interruptions. There's just so much happening today. So as far as the polycyclic compounds, you just need to know essentially like how to tell if something is aromatic. So if we have a ring that's so ugly, it's whatever. If you have a ring like this is multicyclic, so just look at this and still be able to tell, hey, this is a multicyclic compound, but it still has to follow the cyclic planar fully conjugated rule in order to be aromatic. And then if you count the number of electrons, we know we have 2, 4, 6, 8, 10. 10 follows the 4n rule, so this would be aromatic. That's pretty much the extent you have to know. There's also probably going to be a question that asks you something like, which of the following is true of aromaticity, right? And it'll say, like, what are the rules for aromaticity, essentially? It does not have to be monocyclic. So cyclic, planar, fully conjugated, 4n plus 2. Those are the rules. If one of the answer choices is monocyclic, that's not true. Because you can be multicyclic and be aromatic. As long as you have at least one ring, you can be aromatic. And then someone asked what the conceptual material from chapter 15 and 16 would be. So you just kind of have to know the directing effects, and Dr. West calls them the substituent effects. So, for example, this stuff, know the resonance and how the resonance structures affect whether it's a orthopara or a meta-director because of, the minus charge or the plus charge. And then just know, like, all of these groups kind of in order. Know that NH2 is the strongest activator, that NO2 is the strongest deactivator. Know that halogens have their own category because they are orthopara directing, but they're weak deactivators. Things like that for chapter 15. And then for chapter 15, there's a lot of conceptual stuff, and I'll kind of point it out as we go along, but know how to name things like these that we talked about, know how to name these molecules, understand a few concepts that go along with the reaction mechanisms, like here, something conceptual that's very, very important for acetals and ketols is that when you have an acid catalyst, it will go to completion. When you have a base catalyst, it will not go to completion. It will stop at the hemi. Things like that. And then someone said he posted chapter summaries should be studied based on those concepts. Pretty much yes. He posts those summaries, but then he also does like a specific list for the exam, just because he might take out some stuff. So study based on those summaries, but then once he releases the list, like specifically for this exam, kind of shift gears and focus on that more. Name the benzenes. Yes, we can do that right now, because you've been asking me a million times, and I literally forget every time. I'm so sorry. And then only some of these are filled out, because this is all we got to last time in tutoring. We're going to continue this today in SI and stuff. So someone said, how do we know whether one of the chapter 16 reactions will have a base or acid catalyst? So do you mean like whether it will work in acid or base, or what do you mean? Okay, so I will tell you, for this example, or for this reaction, I said specifically, it has to be an acid to go to completion. If I don't say anything, it can work in both. And for some of them, like this one, I'll draw them both out just to show you that it makes the same product, but it goes through a different pathway. So if there's anything special, I will let you guys know. Could it work without a catalyst? Yes, but it's more favorable with a catalyst. So in the acetal-ketol case, without a catalyst, it'll stop at the hemi. But for the gem diol, it will go to completion. It's just not as favorable. Favorable. I don't know why I said that so weird. You are welcome. Okay, so do you guys want to go back to the chapter 15 problems? I know you told me to do one more question, but I completely forgot. Okay, so let's do those benzene common names. Let's open a new page. Okay, cool. So I'm going to draw a couple benzene rings. And we can talk about what their common name and what their, I guess, IUPAC name would be. So give me a minute to draw them out, please. Oh, okay. Sorry, I'm trying to think off the top of my head, like, all of the things that he could possibly ask. Okay, sorry for moving everything around. I just like to kind of group them. Okay, so if you guys need a minute to like draw these out or whatever, I'll give you a couple seconds, but then we're going to go through and name all of these. And I'm going to actually give myself a little bit more space. Let's pretend you guys can't hear everyone in the background. Okay, are you guys ready to get started? Yes? Okay, cool. So, the first one, I believe we have talked about this one before. Its IUPAC name is Methyl Benzene. Do you guys know what the common name is? Toluene, exactly. NH2, I don't believe we have gone over this before. Do you guys know what the common name is? Aniline, exactly. And I really didn't give myself enough space, but whatever, it's fine. IUPAC name would be benzylamine. And I know things are getting cut off as I move across the screen. I will zoom out at the end so you can see them all. Okay, so that was a really good question that someone asked. Like, how do you know whether to put the substituent name before or after benzene? And it just has to do with IUPAC rules. Honestly, I don't remember all the IUPAC rules anymore. He won't try to trick you and say, like, oh, is this methyl benzene or, you know, the other way, benzene, methyl, whatever. It's just usually common naming or a common rule in IUPAC to put, like, methyl, but, what is it called? Methyl, propyl, ethyl, whatever, before the main parent or whatever. And in this case, the methyl is just going to be a substituent like that on the benzene ring, versus here, I believe the NH2 has priority for naming, so it would be the at the end and not at the beginning. I know I struggled a lot to make words for that, but I hope you kind of understood what I meant. Okay, so the next one, first tell me what is this group? What is this functional group? Ether, awesome. So, you guys remember how to name ethers? This one we actually talked about in chapter 13. Not the common name, because I don't think we ever mentioned the common name. So I'll give you a second to think of the IUPAC name. The common name is going to be anisole. Ooh, okay, awesome. So one person said methyl benzyl ether, and one person said methoxyphenyl ether. So this is one of those things where it tends to be super weird, and it can be either of those, depending on what textbook you look at and what rules they follow. For the purposes of this class, I will write both, just in case. Actually, it's going to be methylphenyl. Just because it's directly attached. So, why is my screen flipping out? Methylphenyl ether. Or the other option will be methoxyphenyl ether. And someone said, in chapter 13, I said if there were 4 or more carbons, you would use the methoxy naming. And that is true. Like I said, it kind of depends on which textbook you're looking at. Dr. West uses the 4 or more carbon rule, but the phenyl ring or the benzene ring tends to have like different rules. So it's usually thought of as the parent chain most of the time, and then we just use this as the substituent. So the whole methoxyphenyl ether is usually the favorable one. But some textbooks will actually say no, methylphenyl ether is the more correct naming. Dr. West, last time I talked to him, said either of them are correct, even though he usually uses methoxyphenyl ether. So that's why I tend to give you guys both in this example, because he said both are correct. Okay, so this last one, yes, you could also say methoxybenzene, which might be a little bit more correct here, just for simplicity. Actually, no, I'll give you both. Methoxybenzene. If you really look into it, there's about 1 billion names for all these things. So we'll stop here. All 3 of these are technically correct. Usually he'll either use methoxyphenyl ether or methoxybenzene. Okay, so this one we should be pretty familiar with. What do we call this? This one right here. Exactly, this one is phenol. And one of the IUPAC names, IUPAC kind of names that we could use is benzoic alcohol. But the one that Dr. West tends to use is hydroxybenzene. So the hydroxy group and the benzene. Cool. Benzoic alcohol is not wrong. It's just that hydroxybenzene is the most correct. And that's the one that he usually uses. We could even also call this benzene-all, but we're not gonna even dive down that rabbit hole. Cool. Any questions so far? Alrighty. So, a benzene with a ketone on it. You guys have any ideas? Someone said benzenone. That's a wonderful guess. We're actually going to call it by the most technical name. So, well, actually, first let me give you the common name. So the common name is acetophenone. And this is the aceto. That's where that comes from, because this is like an acetal. And we don't usually really name ketones this way, just commonly, because it's not really the best way to name things. Technically it's the best way, but we in practice don't really like to use it because it sounds super complicated. But the most technically correct systematic name for this would be methyl phenyl ketone. Because we're naming both sides of the ketone. And then someone said, I thought the acetal group was an aldehyde. So the acetal group, yes, is an aldehyde, but this right here, when we have a ketone that has a CH3, that is an acetone. And attached to that kind of acetone group is the phenol group, excuse me. So don't think of it as the acetal group, think of it as an acetone group. You're welcome. Okay, so I'm going to move this because, again, I did not give myself enough space, which is so annoying, but whatever, it's me. So now we have the aldehyde, and we are going to call this benzaldehyde. So it's a pretty simple common name. Pretty straightforward, benzene aldehyde. Cool. And I'm not even going to bother telling you like the correct IUPAC name because benzaldehyde is more than fine. The last one we're going to go over is the carboxylic acid. And so do you guys want to take a guess at either the common name or the official name? Yes, so this is going to be called benzoic acid. And that is the common name. And the, IUPAC or systematic name for this would be benzene carboxylic acid, but that's just literally the same exact thing. So I'm not going to write it down. So, ta-da! Here are our common names for different benzene substituent groups. And I'm going to actually really quickly while you guys write that down. Okay, so according to IUPAC naming, the most correct IUPAC name here will be methoxy benzene. So I will change that just for the sake of not confusing you guys and just giving you the best possible answer. According to the IUPAC website, the most correct name is methoxy benzene. The other ones that we wrote down are technically correct, but they're not the best possible answer, so that's why I changed it. Any questions? Is this good? Are you guys happy with these common names? Makes sense. Okay, cool. So we have like 5 more minutes. Do you guys want to kind of go over the summary of chapter 16 reactions real quick? Excuse me. Someone said, would he give you benzene with multiple substituents to name? So yes, he probably will. But at that point, it's about just being able to know the names of the substituents. So let's say he gives you Okay, let's say he gives you NH2 and a methyl, right? So first of all, what's the relationship between these two groups? Para, someone already gave me the answer. Yes, you are correct, but we're going to go through it step by step. So P for para, and then out of these two groups, which one will take priority in naming? NH2 or the methyl? Yes, NH2, you are correct. So that's going to be the suffix. So we have para, methyl, and then someone please remind me, what is the common name for a benzene ring with an NH2? Benzylamine is correct, but we're going to go with the common name. So aniline. So it would be para-methyl aniline. And then someone asked a really good question. On the test, common name and IUPAC names won't both be answer choices given together. That's absolutely correct. He will only give you one or the other. That's why I give you both, just because either could come up. And someone asked, why go with the common name? Just because if he asks you a question like this with multiple substituents, usually he wants you to go with the common name for the substituent that takes priority. The way, I don't remember who said the IUPAC way, but that one is technically correct. Just the way that Dr. West will ask you 9 out of 10 times, it will look like this. So I just wanted you guys to see it that way. Does that sort of kind of make sense? Okay, cool. Alrighty then. So do you guys want to real quick review the chapter 16 reactions that we had already gone through, or do you just want to call it a day? Someone said yes, please. Okay, cool. So let's go to... No, this isn't it. Okay, here we go. So I have a nice little summary drawn out for you guys already. I will send it to you eventually after we cover it in SI. But the first reaction we went over is the gem diols. So the gem diol reaction is essentially going to be with a ketone, H2O, and either acid or base. In this case, they will both get you the final product. One of the conceptual things that we haven't yet talked about, but I'll just tell you now. In the case of an acid catalyst, it will prefer the ketone form. In the case of a base catalyst, it will prefer the gem diol form. So it will work either way, and these will be at equilibrium. But in the case of acid, it will prefer ketone form. In the case of a base catalyst, it will prefer the gem diol. The gem diol form. Sorry, I read someone in the chat and then I got mixed up. So someone asked, will I make a cheat sheet for chapter 16 like I did for 15? Yes, I actually already made it. That's this file here that I have open. And I will be sending it to you guys as soon as we cover a little bit more in SI. But today is Friday, so I'll send it to you at the end of the day or tomorrow morning, however it goes. I'm actually so excited because this is my favorite chapter and I spent so much time making this cheat sheet, so I hope you guys like it. Okay, so for the acetal, yes I can. Someone said, can I repeat that? So for the gem diol reaction, we have the ketone form and the gem diol form. And when we have acid catalyst, we're going to prefer the ketone form. When we have a base catalyst, we are going to prefer the gem diol form. And I know that's still a mouthful, so I can repeat it again if you would like.
Wait, do you mean like the reaction will favor like the ketone?
Okay.
Like with
so
the arrow?
For the acetal-ketol reaction, it's going to be the same exact thing with an aldehyde or a ketone. So I only drew it once, but we know that it can happen the same way. That kind of didn't make sense. I drew it once with the aldehyde, but we know the same exact steps will happen with a ketone. It'll just be called a ketol instead. So we know that when we have an acid catalyst, in the first step of the reaction, we will get a hemiacetal or a hemiketol. And we know in the second step, we will react one more time. We will get an acetal or a ketol. And we know that in the case of a base catalyst or no catalyst, we would stop at the hemi. And so now I have also drawn out kind of like a summary of acetal, ketol, hemiacetal, hemiketol. So we know if there are two OR groups, an R and an H, we know that that would be our acetal. If there's an R group, an H, an OH, and an OR, we know that that's going to be the hemiacetal. Similarly, if we have two R groups and two OR groups, we know that's the ketol. Excuse me, a hiccup. If you have two R groups and an OH and an OR, we know that that's the hemiketol because there's two different groups up here. And again, we know that this is a reversible reaction. I just kind of got lazy and I only drew one-sided arrows. But I will put a little note that all of these reactions are reversible. Okay, so don't look at the hydrazone. We haven't done that one yet. So the imine formation is essentially going to be a ketone reacting with a primary amine. That's very important. This one can use acid or base, doesn't matter, but acid is more common. So it's going to form the imine, which is essentially just replacing this oxygen with the nitrogen in the R group. And someone said, do they favor any point at equilibrium? So in this case, no. If there is any kind of favoriting anything, I will let you guys know, like in the case of this, where it favored one side over the other. For the most part, all of them are equal, though, besides the gem diol. So that's pretty much it. Any questions before I let you guys go for the day? You are very welcome. I hope you guys have a wonderful day, and I will probably see you in SI at some point later.